Good day, class. We are now on Unit 3 of our biochemistry course, and our topic is on water. Can you imagine life without water? Last October 2016, if you remember the super typhoon Lawin, after that, there were parts of our region without electricity and water supply for a month. And this made us treasure every drop of water in our homes. Just imagine as soon as you wake up, you pee or you poo and there's no water. You perspired a lot after cleaning the fallen debris and fix your house destroyed by the typhoon, and there's no water for you to take shower. And all that we don't usually realize because water is everywhere. In the previous unit, you learned that the human body is 63% oxygen and 25.2% hydrogen. So more than three-fourths of our body is composed of hydrogen and oxygen. And that is, we've answered that in the previous unit, that is because we are mostly made up of water or H2O. There are several uses of water, but here in our biochemistry course, we will only focus on why it is important in our body. So in this lesson, we will look at the structure and properties of water and analyze its relation to of these in our body and its importance as a medium of life. Then we will look at the importance of pH and buffers in our systems. So let's start with the properties of water. What is one thing that is common in all life forms on Earth? Yes, that would be your water. And not even oxygen because some life forms can live without oxygen. But water is common to all. Hence, there must be life forms in planets where water can be found. Isn't that interesting? So what makes water water? The short answer is because of its unusual chemical and physical properties, which all boils down to its structure. So how does the structure of water looks like? The structure of water includes two hydrogen atoms and one oxygen atom. So you draw the molecule like this, and these atoms is what gives water its unique characteristics such as first and foremost, where all other properties of water is associated with is water being polar, where one end is positively charged and another is negatively charged. So just like batteries, so your partially positive charge are those from your hydrogen atoms and your partially negative charge is from your oxygen atom. So in a water molecule, it's just like batteries, the positive and negative charges are attracted to each other. So which makes the molecules stick together. So you have here between hydrogen and oxygen within the water molecule is called a covalent bond. So that means hydrogen, and oxygen, these bonds here are covalent bonds. But if we have another water molecule beside it, the bonds between the partially positive attracted to the partially negative of another water molecule, partially positive, partially negative, uh, these purple lines here are called your hydrogen bonds. So if you have a water molecule here and the other water molecule stick together with another water molecule like this. So you see this phenomenon in a wax paper. I'm sure you've played with a wax paper when you were younger, where water will stick together. Another property of water is that it is less dense as a solid. You see this property almost every day, especially yung mga mahilig maglagay ng ice sa kanilang mga tubig. When you put your ice on your drink and it floats, Compared to other liquids that becomes heavier after it solidifies, like the cement, as you've read from your textbooks, water is different because hydrogen bonds in ice hold the water molecules apart. So as you can see in our example a while ago, these are your hydrogen bonds. Between these are one water molecule, another molecule, and between that are your hydrogen bonds. So this becomes longer. The ice hold the water molecules. The hydrogen bonds in ice hold the water molecules apart, whereas melting, on the other hand, breaks some of these bonds so water can pack closer together. Since water ice floats, it actually helps life survive on Earth. In the winter, we don't have winter here, but when surface temperatures are low enough for water to freeze, floating ice forms a layer of insulation on top of lakes and seas. So this is the liquid water, and this will be your ice. So it actually forms a layer of insulation on tops of your lakes and seas. And this ice layer insulates the water below it, allowing it to stay liquid, which allows the life within it to survive. So if you have fish there or other life forms, they will not be solidified, or they will not uh, be freezing.
The next property of water is a famous one. It is used as a universal solvent. So you witness this property of water almost every day. Our example in our text is dissolving salt in water, which we don't usually do at home, but just to show why, salt is sodium chloride. It has sodium ion and chloride ion. So when sodium comes in contact with water, which is H2O and has positive and negative charges, the chloride ion here gets attracted to the positive charge of water, and the sodium cation here gets attracted to the negative charges of water. And you will see here enclosures. These are called hydration shells. So this property is associated to water's polarity, which allows it to dissolve other polar substances very easily. Now we go to a more realistic example when you add sugar to your coffee. So compared to your salt or your sodium chloride, sugar is non-ionic. It doesn't have any positive and negative charges, but still these are polar compounds. So how does water dissolve sugar? So water readily forms hydrogen bonds with the polar functional groups of sugar. So what it does, it pulls the sugar molecule from the clump of sugars. So they dissolve because the attraction of the solute is stronger between the solute and water molecules compared to the van der Waals forces and the weaker hydrogen bonding in the water molecule itself. However, that is not the case with oil, which is non-polar, so you don't have oxygen and hydrogen atoms here. One group did this experiment very nicely with the title "You Got Me Floating." So when your bulalok cools, oil floats on top of water. Even if you mix it hard, it will still float. Oil floats on water because it is less dense or has lower specific gravity. But it does not mix not because of its density. The immiscibility of oil and water is not related to the difference in density. It is again the polarity. It is the positively charged at one end and the negatively charged at the other whereas oil molecules do not have positive or negative charges. So as a consequence, they tend to stay away from the water molecules. Therefore, oil and water don't mix together. So what is the importance of this property of water as a universal solvent? So we take in so many different kinds of substances, food and other substances, and these needs to be taken in other substances to generate energy and flush out waste products and toxins in our body. So because water can dissolve most kinds of substances, it makes an ideal medium for both tasks, for both energy generation and for flushing out toxins out of our body. So wherever water goes, it carries dissolved chemicals, minerals, and nutrients that are used to support living things. So the next property of water is capillary action. So the typical example for this one is our plants. And hello to all plantitas and plantitas during this pandemic. So a plant gets water from the ground, and water travels up to the stem to provide water and nutrition to the rest of the plant. So what is the importance of this capillary action to our body? Capillary action is important for moving water around, just like in plants, and it is the movement of water in and out of your cellular structure that deposits vitamins, nutrients, and vital blood plasma. So without this flow, your body's cells would not rehydrate and vital communication between brain and body would slow. Again, our next property of water is because of their polarity. Water molecules are strongly attracted to each other, which gives water high surface tension. So the top layer of water acts like an elastic or stretchy sheet because of the attraction between molecules or the sticky nature of the molecules as we just described in the previous slide. So you will see here insects can walk on water because they are light and because there's like a sticky film on top of water, just like also in paper clips. So polarity, surface tension, and capillary action is important to life because it means water is sticky, it tends to clump together, and this allows it to be sucked up as a continuous stream through the roots of plants or circulated through the body, through the blood, the force of gravity. We have additional property that is not seen in our textbook, the high heat capacity of water. So water has the highest specific heat, and that means it takes a lot of energy to increase the temperature of 1 gram of water. So this is again due to the hydrogen bonds between water. And this is important to life because that means that water is very good on holding on heat. So it is hard to heat up, therefore can thermoregulate our body. Hence, water in our bloodstream helps us maintain a constant body temperature.
So for your activity 3.1, illustrate what happens to your hydrogen bonds when water is in ice form and in liquid water. So actually it's already answered in our PowerPoint video. And for activity 3.1.2, actually the first one is activity 3.1.1. This one is activity 3.1.2. Explain the influence of solutes on water properties. Does this reflect colligative properties? So this is another property of water that wasn't discussed in our PowerPoint video, nor it is discussed in our textbook. So knowledge check. What have we learned from this part of Unit 3 or your Unit 3.1 from the properties of water? First, what makes water unique? We've answered that earlier in this PowerPoint video. Second, what are the properties of water? So we listed down a few and another one from your activity. And third, what are the importance of water as a medium of life? So this third question is actually incorporated to your answer for the properties of water. So thanks for watching. See you on the next PowerPoint video on our Unit 3.2 on pH.